In the previous videos, you have learned how to use the Simul8 software to create and run simulation models for MM1, MMC, and MMCN queuing systems. The common features for these systems are that the inter-arrival times and the service times all follow exponential distribution. In this particular video, we're going to show how to use Simul8 to create and run an MG1 queue. In the PowerPoint lecture that I uploaded in HuskyCT, you should have already found out how to calculate the parameters of the gamma distribution, which in this case we will use to represent the general distribution G in the MG1 queue. Alright, so first of all, let's create a queuing model. Now keep in mind that what you always want to ensure is that the distance of your queuing models are set to 0. This is the basic assumption of the queuing system threaded queuing models we have created. Okay. Then usually you want to go to random sampling and check this auto change random numbers at every restart. And some people may prefer not to use this auto restart random numbers, but this is of minor importance. It's just personal preference. So what we do is we can create a model by using start point and then auto-popping this queue, activity, and endpoint. By default, the simulation time unit is minute. And for the example we have, the arrival rate is 2 per hour, so inter-arrival time being 30 minutes. I'll change this to 30. Queue capacity will be infinity since MG1 queue. The activity we're assuming is MG1, so we're going to use gamma distribution in this case. We choose gamma. And of course, we can do this through the property window, like if we go in this way, we'll see the property window like this. We can change alpha, beta in here. In the example where we have these two operators for operator number 1, we calculate alpha equal to 1.44, so I enter 1.44 here. For beta, we calculate it's equal to 0.06, but I mentioned Simul8 made a mistake, and we have to do 1 over 0.06. I click OK to confirm it, and you can see these numbers here also get updated. Then let's set up the warm-up time and the results collection time. Warm-up time, since 30 minutes, let's assume I have about 2,000 customers arriving. So 60 times 1,000, 60,000. Results collection. And change the time unit to simulation time unit minutes. And of course, you can set it to hours, seconds, depending on the simulation scale. Let's do 300,000, so about 10,000 customers will be arriving in the results collection period. We'll click on that. We OK this. Then we need to set up trials. Trial setup. And as usual, I'm going to do 20 trials. Apply. I don't want to see any animations, so drag this all the way to the right. And before running the simulation, if you have in mind, well, I want to know in this case the queue length. So we go to the queue, click on the results, and the queue time and the queue length are both here. We can choose the average number of items in the storage, meaning the queue. Right click, add this to the results manager. And we want to also monitor the utilization rate. So go here, number of work items, and percent of time. So this is the amount of time the actual server is actually busy. Working percentage, right click, add it to the results manager. Then going back, I can click on run trial. let the simulation run. Shouldn't take much time. Okay, so 20 trials are done. The numbers on top of the start point actually show the number of items enter the system for results collection. In this case, about 10,000, as we had imagined. If we look at the results manager, we have the average queue size being 2.76, okay, and the theoretical answer is 2.717. It's sufficiently close. And again, if you want to make it even closer, increase the warm-up time, increase the total results collection time, increase the number of trials. These numbers should improve. But in this case, if you think this is close enough, you have set this up correctly, which is the goal of this particular part of the module, and you're all set. And we can also look at, well, the utilization rate is about 80%. The theoretical number for this part is also 80%, which makes sense. Okay. So this is what we have achieved or calculated for operator 1. And the theoretical answer 2.71, we have 2.76, so close enough. Now if I wanted to look at it for operator number 2, I just have to modify the distribution parameters, which we have calculated, alpha being 156.25 and beta being 1/6.25. Okay. These parameters are calculated in the PowerPoint slides that are uploaded for the MG1Q simulation. Now we're all set. We can run trial again. All the other information or the parameters remain the same. Theoretical answer of the service of the average queue length is 2.097, so about 2.1. And the simulation result gave me 2.07, so very close to the actual theoretical answer. Then the percentage of working time is 83.29. The theoretical answer is 83.33. Again, it's sufficiently close, meaning, well, the distribution parameters are entered correctly. Okay, so with this, we're able to construct, enter the parameters correctly, and run an MG1Q. You may wonder, what if I want to create an MD1Q, or D stands for deterministic, which we also briefly discussed in the lecture. And that's easy. If you want to have MD1Q, you only have to go to the server. D means deterministic, so you don't really need a distribution, but you still have to choose this from Simul8. But in the drop-down list, you will find the one called fixed. Means, as mentioned here, is to have a fixed value, which is the fixed service time. Okay, and let's say, for instance, the second operator, the service time is 25 minutes, so still use 25. So now you have an MD1Q with the service time being exactly 25 minutes for all customers. I'll go back and run the trial again. Since the variability reduces, we should see a decrease in the average queue length from 2.1, in this case 2.09 to 2.07. Not dramatic. That's because operator number 2 already has a very low variability in the service time, being 2 minutes. If we attempt this for the first server, or the first operator, which has a 20-minute standard deviation, but 24 minutes average. So if I change this to 24, to look at how the system performance can improve if for the first operator to completely eliminate the variability in the service. To run the trial again. With the 20-minute standard deviation, the average queue length is 2.7. And with this zero variability fixed service deterministic case, it should be less than 2.07, which is the previous case. And in fact, in this one, the average queue length becomes 1.6. And from these calculations, either theoretical calculations or the simulation, we're able to quantitatively evaluate the effect of changing a parameter of the model or of the system on the overall system performance metric. Okay. And this concludes this lecture.